This is the Unit 7 review covering stoichiometry, including mole-to-mole, mole-to-mass, mass-to-mole, and mass-to-mass problems. And in additional, you will see a section on limiting reactant stoichiometry. Okay, the first thing you always want to do with any stoichiometric calculation is you want to start with a balanced formula equation. And so the proper coefficients to balance this, you need a 4 in front of the iron, a 3 in front of the oxygen, a 2 in front of the iron 3 oxide. Now looking at the problem, I'm going to ask how many grams of rust, which is iron 3 oxide, will be produced if 5.46 grams of iron react. Well, start with what you know. What do we know? 5.46 grams of iron. Well, the only relationship I know between iron and iron oxide is their molar relationship. For every 4 moles of iron, I get 2 moles of iron oxide, or iron 3 oxide. Notice I know grams. So the thing I must do is convert these grams into moles. Well, what's 1 mole of iron weigh? It's its molar mass. 1 mole of iron has a mass of 55.85 grams of iron. You will notice in each step I use units and labels. It helps keep keep stuff straight. Now I have moles of iron. I want to now convert iron to iron 3 oxide. How am I going to do that? Well, I'm going to use the mole ratio from the balanced formula equation. Notice for every 4 moles of iron, there are 2 moles of iron 3 oxide. Moles of iron cancel. If I were to solve at this point, my units would be moles of iron, but I didn't want moles of iron because it specifically asked for how many grams are produced. So I have to do one more calculation, which is just the molar mass. 1 mole of iron 3 oxide has a mass, and if you add them up, it's 159.7 grams of iron 3 oxide. Moles cancel, and now all I need to do is solve. I'm going to multiply across, multiply, and then divide. When I do that, my answer rounded to 3 sig figs is going to be 7.81 grams of iron 3 oxide. This is a very similar type problem, another stoichiometric problem. This time it's asking for molecules. That's no big deal. You know the relationship between moles and molecules. Let's start by balancing this. 2 in front of the potassium chlorate. Let's see, oxygen, you should have a 3. And potassium chloride, you need a 2. So let's start with what we know. 3.75 grams of potassium chlorate. Okay, and I want to go to molecules of oxygen. The only relationship I know is their molar relationship, so I have to convert this potassium chlorate to moles. Well, 1 mole potassium chlorate, if I add up their masses, should be 122.55 grams potassium chlorate. Grams of potassium chlorate cancel. I now know moles. Once I know the moles, I can do the mole ratio. I want to get rid of the moles of potassium chlorate, so I put that on the bottom. For every 2 moles, I get 3 moles of oxygen. And then finally, I know that 1 mole of any substance is how many molecules? 6.02 times 10 to the 23rd molecules. Moles of oxygen cancel. And so what I'm going to do is I'm going to multiply, divide. And when I do this, I get, with 3 sig figs, 2.76 times 10 to the 22nd molecules of oxygen. Another normal stoichiometric problem. We have to balance the formula equation. If I put a 2 in front of the magnesium and a 2 in front of the magnesium oxide, we should be good. He wants to know the mass of magnesium oxide produced from 2 moles of magnesium. So we know we have 2 moles of magnesium. Well, we can go straight to the mole ratio since we already know moles. According to the balanced formula, for every 2 moles of magnesium, we get 2 moles of magnesium oxide. Moles of magnesium are gone. It wants to know the mass. Well, 1 mole magnesium oxide, if I add them together, the mass should be 40.31 grams of magnesium oxide. Moles cancel. I multiply and divide. My answer with 3 sig figs, 80.6 grams of magnesium oxide. For number 4, you're using the exact same formula. This time you're converting from 5.25 moles of oxygen to moles of magnesium, so hopefully you caught that. Let's balance this. I guess it's the same formula. So there's a 2 there and a 2 there. I'm going to start out with 5.25 moles of oxygen. Well, I know for every 1 mole of oxygen, I get 2 moles of magnesium oxide. Moles cancel. I can stop at this point because it's only asking for moles. It did not ask for mass. So 5.25 times 2, and with 3 figs, that should be 10.5, the unit moles of magnesium oxide. Okay, I'll give you just a moment to look over this question. You can pause the video and look at the particulars. I'm not going to actually solve it on this slide because I need a little more room, but this is a limiting reactant stoichiometric problem. You notice I have 2 different amounts of the initial reactants, and I'm asking specific questions about the limiting reactant, the excess reactant, how much of the excess is left over, and how many grams of silver are produced. So as always, the first thing I like to do is I like to balance the formula equation. And to do so, let's see, I need a 2 in front of the silver nitrate. I need a 2 in front of the silver. Everything else should be balanced. What I do is I actually solve the last question first. I calculate the grams of silver that are produced, and then I go back and answer the others. And so there's several ways you can do this. The way I've chosen to demonstrate this to you, I'm going to take 22.9 grams of nickel, and I'm going to convert this to grams of silver, okay? Because that's what the part D asks for, how many grams of silver would be produced. So if I react 22.9 grams of nickel, well, first thing I have to find out how many moles that is. 1 mole of nickel has the mass of, let's see, it's 58.69 grams of nickel. Grams of nickel cancel. Okay, now I can go into my mole ratio according to the balanced formula. For every 1 mole of nickel, there are 2 moles of silver. And then for the mass, I know every 1 mole of silver weighs 107.87 grams of silver. So anytime I have a molar mass, grams and moles, it's always 1 mole. I go ahead and I multiply and I divide. My answer is 84.2 grams of silver. Now, is that my answer? Well, I don't know. I haven't done the second part yet. And so I actually have to go in here and calculate the amount of silver that's produced from 112 grams of silver nitrate. So let's do that. All right, so I have 112 grams. So here are the 112 grams of silver nitrate. Oops. Silver nitrate. And I want to convert that to moles, so I know every 1 mole of silver nitrate has a mass of 169.88 grams of silver nitrate. Grams of silver nitrate cancel. I look at the mole ratio according to the formula. For every 2 moles of silver nitrate, there are 2 moles of of silver. Silver nitrate cancels. And now, once again, I know for every 1 mole of silver, it weighs 107.87 grams of silver. And so I go through and I do my calculations, multiply, divide, and with 3 sig figs, I solve this and it turns out to be 71.1 grams of silver. And so I look at my two results. Okay, so if I have this much nickel, I can make 84 grams of silver. If I have this much of silver nitrate, I can make 71 grams of silver. So how much silver can you make? It's going to be the lesser of the two. So your answer for part D is going to be 71.1 grams of silver. Now, if you go back to part A, we can answer part A. It's asking, what is the limiting reactant? Well, the limiting reactant is going to be the one that produces the smaller amount. So in this case, it is silver nitrate. So there is your limiting reactant. And then question B says, what is the excess reactant? Well, it's got to be the other one, the other reactant, which was nickel. So that was the one that you had more than enough of because you could produce a greater amount of silver, but you run out of silver nitrate first. So the excess reactant is nickel. Now to solve part C, where it's asking for how many grams of the excess reactant, which is nickel, is left over, what I do is there's several ways you can do this, but what I like to do is I will take the amount of the product that you will actually produce, the smaller amount. So in this case, it's 71.1 grams of silver, and what I will do is I will convert this into grams of nickel. And once I know how many grams of nickel it takes to make 71.1 grams of silver, I will subtract that result from the initial amount of nickel. That's the amount that is remaining. So let's go. 1 mole of silver still weighs 107.87 grams of silver. Grams of silver are now gone. Okay, and I know for every 1 mole of nickel from the balance formula equation, there were 2 moles of silver present. Moles of silver go away. I know every 1 mole of nickel has a mass of 58.69 grams of nickel. Moles of nickel are now gone. I multiply and divide, and I find out that to produce 71.1 grams of silver, I need 19.3 grams of nickel. Well, that is not your answer, however. What you need to do is you look back at the initial problem, and it said you had 22.9 grams of nickel, and it only required 19.3 grams of nickel. So how much nickel remains? When you subtract this, 3.6 grams of nickel remain. That is your answer with sig figs. We don't do a lot of subtraction, but when we do, recall that you must round your answer to have the same number of decimal places as your measure having the fewest. Both of these go to the tenths. Your answer must go to the tenths. So it's 3.6 grams of nickel is the excess. Okay, same thing with this problem. I need a lot of space to write it, so if you just want to look at it real quick, you can see the setup and what it's asking. It's very similar to the previous problem, problem 5. Okay, I start these out by, as always, balancing the formula equation. I need 4 nitric acids, I need 2 nitrogen dioxides, and 2 waters. That should be the balanced formula. Okay, so I assume that a manufacturer has 5 moles of copper, 5 moles of nitric acid, and I want to know, if you read the problem before, it essentially is asking how many grams of nitrogen dioxide are produced. So let's start out with what I know. 5 moles of copper, well, I can go straight to the mole ratio because I'm already in moles. So I know for every 1 mole of copper, I get 2 moles of nitrogen dioxide, because that's what it was asking in the problem. Moles of copper cancel. Then I know every 1 mole of nitrogen dioxide has a mass of 46.01 grams. Simply added up 2 oxygen and 1 nitrogen, that's that number. Moles of nitrogen dioxide cancel. I multiply, and divide, and I get 460 grams of nitrogen dioxide. 4 sig figs, so I actually, or excuse me, 3 sig figs, so I should put a decimal after that 0 on the 460. All right, let's look. 5 moles of nitric acid. We're going to do the same type of calculation. 5 moles of HNO3. Well, for every 1 mole of nitric acid, let's see, oh, excuse me, no, it's 4 moles from the balanced equation. 4 moles of nitric acid, I get 2 moles of nitrogen dioxide. Moles cancel. Now I know moles of nitrogen dioxide. I know that every 1 mole of NO2 weighs 46.01 grams still. Moles cancel. I multiply and divide, and you get 115 grams of NO2. So just as before, you have to go with the smaller amount. So the amount of nitrogen dioxide that is actually produced is 115 grams. Now I can answer the limiting and the excess reactant. So the limiting reactant in this case is the nitric acid. The excess reactant is going to be copper. So it's the thing you have more of than what you need. Now to answer part C, when it asks how many grams of the excess is left over, I solve that same way I did last time. I start with the smaller amount of product, so 115 grams of nitrogen dioxide. I'm going to convert this into mass of the excess reagent. And so let's see, for every 1 mole nitrogen dioxide, it weighs 46.01 grams nitrogen dioxide. That cancels. According to the mole ratio, there are 2 moles of nitrogen dioxide for every 1 mole of copper. Moles cancel. And then I know every 1 mole of copper weighs 79.4 grams of copper. Moles cancel. I multiply and divide and solve, and I find the amount of copper required to produce that 115 grams of nitrogen dioxide is 79.4 grams of copper. Now this isn't our answer. It wants to know how many grams of the excess reactant is left over. But guess what? You don't know how many grams of the initial excess reactant there were because it gave it to you in the terms of moles. So the first thing you have to do is find out how many grams 5 moles of copper is. Well, every 1 mole of copper has a mass of 63.55 grams of copper. Moles of copper cancel. 5 times 63.5. Let's see, that should be 318 grams of copper. Well, so that's the initial amount of copper. I only used 79.4 grams of copper. So if I subtract that from the initial amount, you're going to end up with 239 grams of copper that are in excess. Okay, the last problem on this review packet deals with a percent yield. And so the first thing it's asking is the theoretical yield from the following balanced formula equation. If I start with 34 grams of iron 2 bromide. So let's start out with what we know. I know 34 grams of iron 2 bromide. And I need to convert that to moles. Well, I know every 1 mole of iron 2 bromide has a mass of 215.65 grams of iron 2 bromide. Okay, so grams cancel grams. Now I know moles, so I'm ready for the mole ratio. According to the balanced formula, for every 1 mole of iron 2 bromide, I get 1 mole of iron 2 chloride. moles of iron 2 bromide cancel. And now I know for every 1 mole of iron 2 chloride, it has a mass of 126.75 grams of iron 2 chloride. Moles cancel moles. So if I perform this math and I go 34 times 126 divided by 215, you're going to find out, so the answer for this portion, I need to write it down here, is going to be 20 grams of iron 2 chloride. You have to have 2 sig figs because 34 has 2. You had 19.98, rounds up to 20. You must make sure that's zero significant, so put a decimal behind it. For the percent yield part, you have to remember the formula. Okay, so you're going to put this is the formula. The actual divided by the theoretical times 100. So pretty straightforward. And so if you read part B, it says, what is the percent yield if the actual yield is 4 grams? So 4 grams, and the actual will have to be given to you in a problem like this. I mean, if you were doing a laboratory exercise, that would be the amount that you measured on a balance. And then the theoretical is always the amount that you should have got, the one that the stoichiometry, the math told you, this is how many grams or should be produced. So 4 grams divided by 20 times 100, you're going to find out that this is 20% is your percent yield.